All right, let's dive into one of the weirdest and most counterintuitive puzzles in all of physics. It's a question that seems to completely break the rules of common sense.
I mean, just think about it for a second. If you want to make ice cubes, you start with cold water, right? It just feels obvious. But what if I told you that under just the right conditions, starting with hot water could actually get you a block of ice faster?
And get this isn't some new theory cooked up on the internet. Nope, this is an ancient riddle, something that people like Aristotle were pondering over 2,000 years ago. For millennia, we've been trying to figure out if this effect is even real, and if it is, how in the world it could possibly work. But before we can even get to an answer, we have to talk about why this is such a nightmare to test in the first place. And it turns out the problem is the experiment itself. It sounds like a silly question, but what does freezing actually mean? Is it the moment the very first ice crystal shows up? Or is it when the whole thing is a solid block of ice? Believe it or not, your results can be wildly different depending on how you define it. So, to be consistent, scientists are on the lookout for one very specific moment. See, when water gets super cooled below 0 degrees, it's still liquid. But when it finally decides to snap into ice, it releases this little burst of energy. It's called latent heat, which actually makes the temperature jump up for a split second. That little spike is the signal they're waiting for. And check this out. This graph shows 8 different temperature readings from inside the exact same container of water. I mean, look at how different those freezing times are. Just moving the thermometer a few millimeters from the top to the bottom can completely change the result you get. And this really highlights the core issue here. There are a ton of variables. As one scientist, Monwia Zheng, put it, the results can depend sensitively on any of these factors. That makes getting a clear picture almost impossible. The shape of the cup, how pure the water is, how much evaporates, any one of these things can throw off the whole experiment. But okay, let's just say, for the sake of argument, that you could perfectly control for all of that. Is there a physical mechanism that could actually explain the Mpemba effect? Well, one of the leading theories revolves around that weird property of water we just mentioned, supercooling. So, this graph here shows what you'd expect 99% of the time. The cold water, that blue line, hits freezing long before the hot water, the red line. Simple, right? Case closed. Well, not so fast, because in another experiment, the exact opposite happened. The hot water froze first. The key is to look at how far the temperature drops below 0. The cold water had to get all the way down to -8 degrees before it finally froze, but the hot water, it only had to reach -6. And this brings us right back to that key concept, supercooling. Water doesn't always freeze at a neat 0 degrees Celsius. It can actually stay liquid way, way below its freezing point, just kind of waiting for the right trigger to turn solid. You see, this changes everything. The race isn't to 0 degrees anymore. It's a race to each sample's own special freezing temperature. And as we just saw, those can be very, very different. Now, the reason for this is something called nucleation sites. Just think of these as microscopic impurities in the water, little bits of dust, bacteria, whatever, and they act like seeds for ice crystals. Each of these seeds has its own specific temperature that will trigger freezing. The water will only turn to ice when it gets cold enough to activate the best, warmest seed that it has. So here's how the whole theory works, step by step. 1. You start with 2 water samples that just happen to have different seeds in them. 2. Here's the key part. The theory suggests that when you heat one of the samples, you actually destroy its worst, coldest seeds. This leaves it with only the better ones, the ones that trigger freezing at a warmer temperature, say -5 degrees. 3. So now, even though that water starts out way hotter, it has a shortcut. It only needs to cool down to -5 to freeze, while the other sample has to keep going all the way down to -10. That gives the hot water a chance to win the race. It's a really cool theory, right? But there's another possibility. What if the Mpemba effect isn't a strange property of water at all, but is actually just the result of a botched experiment? The skeptical argument is pretty straightforward. The people who claim to see this effect simply aren't controlling for all those little variables we talked about. They believe something else in the setup is creating a total illusion. So take this experiment from a researcher named James Brownridge. He put 2 copper cups in a freezer, one hot and one cold. Both were sitting on a thin layer of frost. Well, you can see what happened. The hot cup immediately melted the frost right underneath it. And that tiny little puddle of water, it changed the entire game. Water conducts heat way, way better than frosty air. So all of a sudden, the hot cup had this direct, high-speed connection to the freezing cold floor, letting it dump its heat way faster than the cold cup, which was still sitting on that insulating layer of frost. It was an illusion created by the experimental setup itself. It's sneaky variables like this that lead some scientists to be, well, pretty blunt. A team from the University of Cambridge ran their own super-controlled experiments, and they concluded that once you get rid of all these external factors, the Mpemba effect just vanishes. So where does that leave us? On one hand, you've got a plausible theory with supercooling and nucleation sites. On the other, you've got really strong skepticism about experimental errors. So what's the final verdict? Is the Mpemba effect real or not? So the whole debate really boils down to this. Is it a genuine phenomenon, something driven by changes inside the water itself? Or is it just an illusion, a kind of ghost created by a poorly controlled experiment? Well, the most balanced verdict seems to be this. The effect isn't impossible. It doesn't actually break any fundamental laws of physics. But, and this is a big but, it is an incredibly fragile phenomenon. That means it's super rare and really, really hard to reproduce on demand. For the Mpemba effect to actually show up, you need the absolute perfect storm of conditions. The right impurities, the right containers, the right cooling environment. The fact that scientists are still arguing over what that perfect combination even is, well, that's why this 2,000-year-old question is still so compelling today. It all just makes you wonder, doesn't it? If something as seemingly straightforward as water turning into ice is this complicated, what other simple scientific truths that we all take for granted are hiding a much deeper, more complicated, and way more fascinating story?